Today we are going to discuss on a blast furnace thermal control, and primarily here we will be focused on a fundamental shift in how we manage the this thermal control in the furnaces. So traditionally we have been a reactive, waiting for the hearth to tell us it's cold or hot, but by then the damage is done. So if you look at the title slide, you will see a high-tech cross-section of a furnace. Notice the two data points on the right. The orange dots for the hot metal temperature at 1500 degrees centigrade. That's the reactive side, what we have always used. But look at the glowing blue gas stream on the left. That's our new focus. It has you at 0.92. That is our proactive indicator. Today I am going to show you how to use time average data CO and delay logic to stay ahead of the thermal curve. So, uh, why we need this new approach? We have to talk about the furnace's greatest challenge. It's and that is of its own. So, coming to our next slide, the enemy is the thermal inertia. The enemy we face every day is the thermal inertia. Think of a blast furnace not as a simple heater but as a massive thermal flywheel. You cannot pilot it by looking at the rear view mirror. See that sports car in an instant system, the stopping distance is immediate. But look at the bottom graphic. Our furnace is like that heavy vessel trailing a massive wake of a rear view thermal inertia. By the time you detect a thermal drop in the cast house, the actual deficit started at the top of the furnace 8 to 12 hours ago. If you wait to feel it cool down, you are already locked into a chill. So if we cannot rely on just feeling the heat at the tafel, what should we be looking at on our dashboard? So the thermal dashboard, which contain mostly are the core parameters. So this slide shows the 5 core parameters we need to balance. So first status Q or the gas utilization, this is the ultimate leading indicator. It tells us how efficiently we are using gases to reduce ore. Then we have a direct reduction or DR. This is a massive heat sink where solid coke reduces FeO. Now in the center you will see the scale. We are balancing exothermic fuel burning against the endothermic direct reduction. Finally, look at the bottom. We have silicon and hot metal temperature. These are lagging indicators. If the silicon is dropping, the furnace has already cooled down. When that balance in the center of the dashboard tips towards the endothermic side, a dangerous cycle begins. And in the subsequent slide, we are going to discuss the heat balance engine, why the furnace cools. So let's look at the heat balance engine. This is the critical. The rule is that 80 to 90% of the heat in the Bosch gas is consumed by direct reduction. If we lose efficiency, we enter the self-accelerating chill cycle shown in the circular diagram on the right. It starts with the DR increasing, which consume massive amount of heat. This makes the material colder, which causes even more direct reduction. This cycle can cause a furnace to crash from normal to freezing in just 2 to 8 hours. Once it accelerates, because this cycle moves too fast, we have to change our entire diagnostic strategy. And coming to these diagnostic strategy, uh, uh, reactive versus proactive control. This matrix highlight the old paradigm versus our target state. In reactive control, we look at the hearth. Our response time is 7 to 12 hours. Let because we wait for the chill to manifest at Tafel. Now look at the blue box. On the right, proactive control. Our metrics are eta CO and directed action. We are not looking at the heart, we are looking at the top gas and the cohesive zone. This gives us a instant, very fast read on the furnace's heart and health too. That is the thermal health to the specific. We adjust our PCI based on the gas trend before the body even reaches the melting point. So to make those adjustment effectively, we have to account for the physics of how material and gas moves. So now coming to the visualizing the descent for better understanding which are built in uh, uh, delay logic. So think of the furnace as having two different clocks. On the left we have the top down delay. When we charge the coke rate at the top, it takes over 12 hours to reach the raceway. This is for long-term baseline corrections. On the right is the bottom-up path. By injecting pulverized coal at the 2 years, we get a much faster response. The delay to cast house is only 3 to 6 hours. This is our tool for immediate thermal control and breaking that chill cycle we just talked about. Now let's zoom in on the most important tool in our proactive toolkit, the eta metric. So the master metric eta as the leading indicator. Eta is our master metric. As you see on the formula at the bottom, it's the ratio of CO2 to total of CO and CO2. Our green zone where we want to be in between 45 and 50%, that is towards that blue, towards this point. A rising eta means we are efficiently removing oxygen using gas which saves coke. Point to the orange part. If you will see this part, uh, but dropping eta is a warning. It means gas reduction is failing and the body is being pushed into the lower furnace unreduced. That forces the furnace to use its thermal reserve for direct reduction. But as any operator knows, the raw gas data can be incredibly noisy. So filtering the noise, the time averaging strategy. If you react to every single raw data point, you will drive the furnace crazy with overcorrection. So look at all that grey noise in the background. Those are single top gas reading fluctuating with every change. Our solution is the layered moving average. Look at the three lines. The 24 hours average sets our stable baseline. The 16-hour average identifies the macro shift, and the 8-hour average, the bright green one, reveals our immediate trajectory. The rule is do not chase the raw data, chase the 8-hour trend line. When we watch that 8-hour line closely, we can spot the moment the furnace start to slide. So identifying the thermal cliff, this graph shows the signature pattern of a looming disaster. This is our action window. Notice that at this exact moment, the hot metal temperature at the bottom, the orange line looks perfectly normal. Everything seems fine, right? Or wrong. Look at the top graph. The 8-hour eta has dived below the 24-hour average. The thermodynamics are already locked in. A severe chill will hit the cast house in 4 to 6 hours unless we take action right now. So, what exactly is that action? We have standardized it into three scenarios. And what are these? Built in the thermal control rules, we have three main scenarios as we have mentioned. So, coming to the point one scenario, as it's shown, if silicon or hot metal is trending down but it is stable, it's just a minor deviation, a small PCI increase fixes it. Coming to scenario number two, this is our proactive correction. If ATASIO is trending down over 8 hours and the burden is accelerating, we make a preemptive PCI adjustment of up to 10 kg per ton hot metal before the hot metal drops. And now scenario 3, if you see a long-term deficit across the 24-hour average, we have to adjust the coke rate at the top. So most of the time these rules keeps us safe, but sometimes the furnace gives us a red button warning. So coming to the recognizing a red button scenario, you need to know when the standard small adjustment would not cut it. We call this the red button scenario. It's marked by a massive deer spike, a runway burden descent where coke is burning too fast, or a sharp simultaneous drop in both silicon and temperature. In these cases, a small PCI tweak will be sorted whole by the heat deficit. You must break the cycle immediately. Here is the four-step emergency procedure for when that red button is pushed. The red button procedure. So step by step recovery. When things get critical, follow these four steps. Boost PCI instantly by about 20 kg per ton hot metal to provide immediate carbon. Point number 2. Protect your flame temperature. Don't let it drop or you will compound the chill. Point number 3. Charge coke blank from the top to replace lost thermal reserve, even though they will take 12 hours to arrive. Finally, towards 4, point number 4. Finally, if the pressure drop is too high, reduce the blast volume to stabilize the descent. By following these rules and focusing on the gas, we move into continuous cycle of stability. So the unified proactive loop, if we talk about, is to wrap up, is basically wrap up. So let's look at the unified proactive loop. We monitor the 8, 6 and 24 hours ATASIO. We predict the chill by watching the increasing direct reduction. We adjust using PCI with that 3 to 6 hours lead time. And finally, we confirm our success by looking at the HMT, hot metal temperature, at the hearth. So our final takeaway today is this: great operators don't fix cold furnaces. They read the gas to ensure the furnace never goes cold in the first place.